Okay, thank you, Marius, for the introduction. The bar is set very high now. Hope I can, I can fulfill the expectations. Anyhow, okay, so the topic that I'm going to talk about is cleaning for ML, like ML in terms of machine learning, of course. I guess I don't need to introduce that abbreviation in this summer school. But nevertheless, as Marius said, I'm from the databases, just so I have a quite data-centric view on the whole pipeline, on the whole AutoML pipeline. So we look at how data affects the outcome and how we can change data or prepare data or improve data so that everything what comes after in terms of an abstract application, which here it can be just a machine learning application or just or more concrete an AutoML framework can work better. And I will also talk a little bit about the interaction of cleaning and AutoML within my talk. But just to set the stage, right? So this is a very old slide of mine that I use since 2016. But the headers that I have on this slide are actually even from much earlier, from 2012 and 13, where the big data hype began, right? So before all the other hypes came later with neural networks and now AutoML and so forth, it was data. So data was in the beginning. We had big data as the new resource for new applications and value for all sorts of applications. And in the middle, there is this persona of the data scientist who somehow has to be able to deal with big data, either be it as an engineer to engineer pipelines and databases, or as a statistician who is analyzing the data and trying to generate insights, or as most of you might like the way you would see a data scientist would be as somebody who is also proficient in machine learning and all the technologies that are accompanied with that. So what I usually then do is I also ask this question. And by the way, feel free to interrupt the talk whenever you want. So whenever you feel I'm leaving you behind or something, just raise a hand or give me a sign so that I can talk to you. So this is a typical question that I have, is like what data scientists typically do, right? So during their work, and you're free to answer if you want. Otherwise, I will just continue. So how were the other sessions? Was it very interactive or?
So normally we're using Slido actually for asking questions. So we have a Q&A at the very end, but of course you are free if you'd like to have more direct interaction with everyone already now. Please do so.
Okay, sure. Maybe it's too early, so I will just continue at this point with with the answer, right? For somebody's writing something, so that's
that was me only providing again.
Oh, that's only you. Slido. Yeah, boring. But okay, what was that Slido? What's that? Type of question. Okay, interesting. Cool.
So the people can then upvote actually questions and so on, and maybe have a nice overview. Cool. It worked very nice, actually.
So it turns out like the big reveal is that most of the time the data scientists are busy with work that is not so interesting. So basically collecting data sets and preparing, organizing, cleaning, and building all the framework that is required to let their fancy models and applications run on them. Like, so it's not that those parts are easier. It's just that before you get there, you need to do all of that unpopular work. So this is a survey from 2016, but there are also later surveys that kind of confirm this view. And we will also see here the Gardner hype curve for 2021. So this is typically a curve that kind of lists all the new technologies and hypes that are around and puts them into context with regard to how hypey they are, kind of. So you can imagine 10 years ago, big data was at the peak of inflated expectations. So you see at the bottom, the different areas. It starts with an innovation trigger. So everybody's excited with a new idea, then there is high expectation and it's kind of inflated. So more expectation than what is probably possible. And then the hype goes down. You have the trough of disillusionment. And then slowly those who were really serious about this technology will work towards something that works, right? So that's a slope of enlightenment and later plateau of productivity, as you can see it here. And even now, years later than the beginning, you see some terms popping up again. Like here you see augmented data quality. That's one thing that's interesting right now to many people. And at the same time, we have data preparation tools already in the phase where people are really making efforts to create something that works and that is useful. And other similar areas that kind of relate to that pattern are everything that has to do with metadata management and data lakes. So if you have a large unorganized database in your organization, you call it a data lake as soon as you don't know how everything connects and as soon as there is no specific workload that is always accessing the database for information update and needs. So it's typically just a storage where people put their data. So my favorite example of that is from pharmaceutical companies or companies that do deal with sciences. So typically they have some sort of trials and experiments during the time of a scientist at the company, and all of that data goes into a lake. And then the scientist gets a better job at a competing pharmaceutical company, leaves, and the data is still there. It has information that can be used for all sorts of applications, but nobody knows anymore how the data, what the context of the data is and how it can be used. And that happens a lot. So you end up with having large data lakes that require post-processing to understand them because the people who are in charge are not there. So you see the whole data quality problem is also tied a lot to the people who are stakeholders in this area. Nevertheless, because of that situation, we have the great opportunity to do research on how to automate the process. So, like if you imagine that everything was perfect, everybody would provide perfect data for a use case, make sure that everything is usable later, everything would be easier and we wouldn't need many of the automation solutions that are necessary right now. But that's fortunately or unfortunately not the case. So typically in this process, you have like the raw data on the left-hand side, right? So this can be a relational database, it can be non-relational data, it can be simply sources where data are coming right away from the sensors, or it can be an application on itself that is producing data. And before you can get to the right-hand side, which contains like the analytical tools, including the machine learning or data science platforms, you need to go through this process, right? So you need to discover the parts of the data that are interesting to you. You need to identify the structure of the data so that it's parsable and fitting for the application. That's called profiling. And then you need to do all sorts of cleaning operations that can contain transformation or matching of values if you want to get rid of redundant and duplicate values, or you want to get rid of undesirable values within your data sets, being it null values in the very simplest form or just some typos or something else, right? And this process takes a lot of time that is not interesting. So Michael Stolbreaker, one of the pioneers of the database research, was like the creator of Postgres and Ingress and so forth. He found interest in data integration like 10 years ago. That's why I was also joining MIT during that time. So he is calling data integration the 800-pound gorilla in the corner because it's scary and it's just sitting there and nobody wants to move past it. And everybody has to do with that. And that's basically the motivation for our research, which is aiming at hiding the complexity in this process. And that's possible through reuse of artifacts and enabling domain expert supervision. Because if you imagine that you are somebody who knows the data, you are like the domain expert, you are the biologist or chemist, maybe you are you have done computer science and biology together, but everybody can just have a subset of the knowledge that is necessary for these kind of applications. And you don't want to know everything from database extraction until model tuning over to interpretation of data. So that's basically the motivation to try to make these processes easier and to reproduce. And you can also not always guarantee that you have such a large team where everybody has a dedicated task so that everything can follow up properly. So you need to somehow make this process easier. So basically trying to tame the gorilla in the middle so that you can move past it easier. So in this talk, I will particularly talk about data cleaning. Now with a definition, you will see other definitions of cleaning, but the one that we use in our line of research is cleaning was referring to fixing data points, which means we find data points that are erroneous based on some sort of ground truth understanding that we have on the data. And we try to figure out how to efficiently clean them to the correct values. So that encompasses a bunch of work that we did in the last year. So first, to give you an overview, I will talk about some traditional approaches that exist in the literature for cleaning or how it is just simply done. And then I will move over to two of the systems that we created within our group and set the stage for some like the vision that we have on how cleaning could further be simplified in the machine learning application process. So before I go there, here's again like an overview of the group members who heavily contributed to everything that I'm saying here, in particular also some of the slides. So two of them have already finished, but Felix and Fatime and Binger are still working on that area. Okay, so what is a naive solution for cleaning data for an application is you just independently from whatever application you have is you just clean it based on whatever you consider as cleaning metric being correct or not. So you pick your original data set, that's the dirty data, right? It has mistakes. And you use one of the existing works. This can be our systems, Raha and Baran, or some other research projects, or even some vendors that have wrangling tools. And the output is hopefully a data set of higher quality, where you have fewer mistakes, fewer missing values, and a more complete and concrete and correct data set. Right, so far so good, but it has no implication, or it has nothing that is tied to ML at this point. So the question is, we will answer the question to which extent it plays a role at all that we have machine learning at the end of the pipeline. So should we do cleaning always the same way for all applications or not? That's a big question here. Okay, so traditional cleaning is quite simple. So basically, whatever you find about data cleaning from the last 20 years up until, let's say, 5 years ago, where more machine learning applications were included, were either rule-based techniques, so you had a bunch of constraints. This could be simply functional dependencies or some logical structure constraints over your data. And you just parse your data through these constraints, such as the zip code has to functionally determine the city name, and you set a trigger or alarm when that's not true, right? So whenever you see the same zip code with two different city names, you say, oh, something must be wrong, right? And you see already there is a problem. We don't know what exactly is wrong, whether the zip code in one column is wrong or the city name. So that is not possible to say. There are a bunch of heuristics to maybe figure out and pinpoint the actual source of error. You could say, okay, I will check how my data points are violate, how many rules they are violating at the same time. So then maybe I can decide which point to clean first, right? So that's one way to think about it. Then you can do the same thing with the constraints on a much finer granular level, namely on the string level. you can say that values on a specific column have to have a specific pattern. So you can, for example, think of emails or credit card numbers. So already while you are filling out some forms, they do some quality checks, in fact, right? So it's easy to check for syntactic features while entering data. You will see that it's still not always working. So one of my famous examples is that when we were updating the passport of my wife at the Bürgeramt, they just mistook an I for a 1, and that was in the passport. So it's not something that is guaranteed to be there, right? So, and then you notice it later at the airport that the numbers do not fit with what is on the record. So these are other constraints that you can use. Or if you have numbers, so that's very common for sensor data or measurements or something that you are reading continuously. You just use some outlier detection methods, right? In a way, an outlier is a good heuristic for an error, right? So an outlier per se is not a data error. It can just be an unusual point. But the idea is to say that whenever we have unusual points, the likelihood that they are maybe wrong is higher, right? So you should look more often at outliers. And in fact, we had a study where we compared all these methods, and it turned out that for most data cleaning techniques, statistical approaches are not so reasonable because data errors happen more often. They are more usual than unusual, let's say. So it's maybe a bad prejudice towards data errors to think that they don't happen that often. And that's why they are a big problem. So if you imagine, like, if it was only one data point among millions of records, probably nobody would care that much about automated solutions. But typically, the degree of dirtiness that people talk about is between 2 to 20% of the data, and that's far higher than any outlier could be detected, right? And finally, you could have some sort of master data or knowledge base where you have data aligned in a proper way, where you know this is something that I call ground truth, and you just cross-check your own data set with that source. You figure out whether the entities are in the right relationships, whether there are contradictions with this master data, and you can detect it. So you can, and then you can combine all of those the way you want, but these are like the basic and prominent approaches that are out there in the literature and that you can use for automated techniques. There are also interactive techniques, so especially there's like the company Trifactor, who has like this wrangling approach with data. So you try to look at the data and try to manually enforce your patterns by working with the columns and the separators and generating scripts that way. It's also a way that something that you might also have seen in Microsoft Excel, where you can kind of simulate a script by saying how points have to be changed to other values or column values of one column in the other column. So you extract proper information, and it tries to deduce the script for the extraction, right? So there is like some interaction between extraction and cleaning, basically saying, give me the clean part of the value from this set of columns, right? And put it into column HI or something. So state of the art, right? So then we have a bunch of companies who say, yeah, data quality is really important to us. So we would like to kind of fix it. And then we have people who have done research and built systems in the past year. And these are the data cleaning experts with the right tools, right? And they come and showcase how cleaning is performed. They show you a common data set, which is like the flights data set. Is a real world data set where you have real errors and you have also the ground truth. By the way, that's a very big problem in the research community for data cleaning, to have real world data sets where you can try to reason about how cleaning can be generalized or not, right? So there's a lot of generated data, but some are real. One of them is the flights data set. Anyhow, so they show that to the stakeholders, say, look, you have this data set, and then we load the data constraints into the system, and we choose a bunch of detectors, right? So you see here, there's detect null detector, detect violation detector, and some detector, and they should detect the errors. And then we set up all the featureization operations for repairing the data. Now, the first thing that is interesting is like the domain experts will say, well, that's great, right? So what are the data constraints, right? So who is giving that to us? And then you start as a data engineer, and this is a true story. We had that with one of the real world clients at MIT when we talked to them about cleaning their data. We talked about them and said, can you give us some of the functional dependencies in your database? And everyone was looking at us, what are functional dependencies? And what do you mean with errors? So you have to understand that domain experts just don't use the same vocabulary. And they also don't have the same way of thinking what is a correct value and what not, right? So in their world, correct is something that has been approved by a person, right? And not something that is somehow generated one way or the other way, or one way or the other way. So you have the first problem here, because then you say, yeah, these are the typical constraints that you have to define, because we don't know them. We only have the tools, right? We wouldn't know how the data, what are the consistency issues. You have to try to express them within the language here. And the language for a computer scientist is not that difficult. Basically, it says tuple 1 and tuple 2. For them, it should the flight values should be equal, and the scheduled departure times shouldn't be equal. So whenever that happens, we see that the denial constraint is activated, right? So we cannot have different departure times for the same flight, right? So that's what this rule expresses. And you have a bunch of rules below that. Anyhow, so that's something that the domain experts have to know, but they probably don't know all the rules about their data set, and in particular, they are not willing to encode all of that. It looks complicated, we don't want to do that. And especially if you have machine learning approaches, that comes at you as well, right? So a bunch of parameters and thresholds that you need to set. That's also not something that people are happy about. We don't want to do that. And configurations, you have them for all the traditional approaches as well. So for the rule-based technique, somebody has to give you the rules. For the pattern-based technique, somebody has to give you the patterns. The statistical techniques require you to set at least the mean and variance expectations if you have some Gaussian distribution that you want to check. And master data, even more difficult, somebody has to give you some sort of clean data. So that's a big problem. And typically what the person says, oh, we don't have all of that. Can you still clean our data, right? So that's the demand. So the only thing that remains for you is to say, okay, there's like this new trend, it's called machine learning, right? So what if we knew some values are correct and not? And oftentimes, you know that machine learning requires a lot of training data. So we end up having the original problem that somebody has to clean large chunks of data. So that's not good enough. We need something that works with very few examples, right? So that's basically, you could, and I had this discussion also in classes where people said, isn't like matching records just clustering? Or isn't cleaning not just a classification task? Yes, like theoretically you could do that, but the sensitivity of the factors that play a role here are very different. You cannot expect to have the same resources compared to other tasks where you might have some tagging systems available or where you can generate proper data. So the idea is that the user, who is a domain expert, gives us the domain expertise. They tell us what to clean, and they don't need to tell us how to clean it. And that's basically the example-based approach that we are preaching since a while. So ideally, the user cleans a few instances and the system detects remaining errors. Sounds good, right? So it sounds like something that would make sense if it works. For that, we need to somehow discuss what a data error is by definition. And as it is in each context different to specify, we have the very vague definition of saying a value that is deemed to be incorrect and undesirable by the user, right? So somehow the user has to give us insights on that. And there are some head problems, like all the formatting errors and spelling mistakes are probably errors in all contexts, right? So whenever you misspell something, you should know that it's wrong, and you can use generalizable tools for fixing all of those. So these are not the biggest problems typically, unless you have very weird formats in your data set that are allowed, then it becomes a problem. Usually you have the tail problems that are not so easy to fix. They depend on the semantics of the data and the context. Like the hardest data set that we had in the past to clean was a data set that only contained tags, right? So you can imagine there is no semantics information, there is no structure information. Okay, there is some structure information. We would know how many characters the tag would have, but we wouldn't know which tag belongs into which cell, because we lack the expertise of figuring out how these tags relate. And the tags were, and it was basically an observation data set about fires in forests and what animals they observed that were fleeing or jumping around or whatever. So it was some sort of observation study where the data was filled in with tags, probably because it's shorter, I don't know. Anyhow, that was a difficult one. And if you have worked with SAP databases, you will see a lot of tags there as well. So that's a typical problem. So when you want to achieve that, when you want to say, I want to do example-based cleaning, where I only clean a few examples, the first question is, how do you represent the instances so that you can rely on the fact that the examples that you covered are expressive enough for the rest of the data set, right? Because one detected typo does not necessarily generalize to all possible typos in a data set, as a very simple example. So if I show you that Berlin should be written in a different way than it was in the data set, it doesn't tell me necessarily how a misspelling of Stockholm should be treated, right? So it's not that obvious. The other thing is, which is kind of related to that, how do you pick the instances? So what should they cover? And in particular, you are interested in picking probably dirty data over clean data, because you want to have some information on how something should be cleaned. And you want to pick different types of dirty data. So cleaning two instances where you just clean Berlin from written with double N to one N is not helping you that much. So ideally, you want to cover two different data types when you are labeling two different tuples. And then finally, the question is, how would you model the classification task? If you have, for example, detection, it's a bit easier because you can just have a classification task that decides for every value cell whether it's erroneous or not, right? You could make it even more complicated to give a probability and try to have a semantics on the probability on that. And if you want to correct the value, it becomes much more difficult, because then you somehow have to restrict the type of classes that could fit for a data cell. And in theory, you have unlimited classes for a prediction for one value cell. So it's a bit tricky to think about that, but that's something that you can put your head around. So that leads us to the second part with Raha and Baran, where we try to address these challenges. In particular, this is a system that has been developed like consecutively. First, we built the Raha system for detecting errors. So basically, you got an input data set and some labeled tuples, and you got like the table on the right-hand side where we have marked all the erroneous values, right? Below, you see also the corrections, like the correction rules that were generated by Baran, but we will talk about that later. So that's what we want to have. We want to have a system that takes as input a data set, some labels, and outputs the dirty data set plus correction suggestions. And this is, by the way, a system you can just try out. So you can just pip install Raha and see whether it works on your data set, and let us know if you notice something weird. So that's something that is useful. Let's talk about the different engines, like starting with Raha. And by the way, with pip install Raha, you get both. You get Raha and Para. It's just historically under that name. So we are now here. We just want to figure out which values can be marked as errors and which not. And one of the bases for building that system was one of the insights that we gained in 2016 in a paper where we compared different types of traditional detectors, like rule violation detectors, pattern violation. As you can see here, it's some sort of diagram. It's not a Gantt diagram, but I don't know how to call it. I didn't find the name yet. But basically, each number in each area tells us how many of the errors in the data set were detected by the overlaying tools. Like if this green area covers all the errors that were detected by outlier detection, and the blue area, everything that was covered by pattern violations, we can say that 19,197 errors were detected by both of them and the rule violation component. And you see that some errors are like in these corner areas. In particular, here we see a lot of them, right? So what is the message here? We need all the signals. It's not enough to just rely on one signal. When you have a random data set, you need to include all signals for your detection. So whatever detection tool you build, you need to consider these different types. So possible directions were in the beginning, obviously, somehow aggregating all these tools. So we could do a majority voting or some sort of quorum threshold to say, okay, if at least K tools agree on a value to be an error, we consider it an error, right? And then you have a trade-off. The higher you choose K, the higher will be your precision in detecting errors, but the lower will be the recall, because most of these tools will not overlap always, right? So basically you would only get, if you pick like K equals to 5, you would only get these number of errors. And if you pick K equals to 1, you would get everything plus all the false positives that come along, right? So there are a large number of positives. That happens when you just union each tool. We tried out semi-supervision. We tried the best combination of the detection techniques with different weights, learned through a classification task. It worked better, but it needs training data up to 1%, right? Now, I would say 1% doesn't sound high. Like typically I have tasks where I have 60% training data and 40% test data or something around that, or maybe 80-20. 1% is great, but it's not, right? So somebody has to clean that data. It's within some company. You cannot use crowdsourcing for that, and it's very expensive to have that training data. So that's a big problem. And another overarching problem is still somebody needs to configure now 5 different tools at minimum, plus the machine learning task that is on top, right? So we have 2 big problems that we wanted to solve. So what if we could generate the configurations automatically? Then we would get rid of the first problem, the second problem that I mentioned. And the other thing is, can we somehow boost the labels that we obtain? There is technology through active learning that helps a little, but ideally, if we want to reduce the number of errors, one has to ask themselves, what is the minimum number of labels I would need for a data set in theory? And basically that's the number of error types that I have in my data set, or at least the types that are kind of distinguishable from each other. Because other than that, there is no chance that I can cover everything, right? So I would need a label for each type. That's the minimum that I need. And it turns out the number of types is not that high in a data set. So typically you can end up with very good performance with 20 labels or so. So what was the idea? The first thing is we don't try to find tools that fit our solution. We use all tools available. We generate all sorts of configurations automatically. So that's easy, because the moment you say all, you can just have a script that generates everything. And we use the output of those tools as signals, where we embed the values, right, of a data set. And these embeddings can be used to cluster the values, because right now we don't know which tool is working well to detect errors in one data set. So they could say yes and no on an unexplainable basis. But we can say that some values are similar in the way they were evaluated by an algorithm, right? So they are similar in that we still don't know whether they are similar because they are correct or whether they are similar because they are mistakes. And that helps us to identify the clusters. And then we just ask for labels per clusters, right? It's not necessary anymore to label data points randomly without any information about what's happening. We have clusters that tell us how values are similar to each other with regards to the data quality signals that they emit. So to have these signals, we picked the most prominent categories of detection techniques that I showed you before, and we generated all configurations systematically. So for each algorithm, we have a bunch of configurations. For rules, we just generate all sorts of column dependencies that exist. For statistical distributions, we have some threshold, some interval of parameters that we use to generate all sorts of tools, and we end up with a bunch of detection strategies or detectors. So here's one example of how it could work. Imagine we have the column city with some values. You see some values are correct, Berlin, and we have a typo here, so here's a missing value. Then we have a hidden missing value where somebody just entered something, and we have two typos as well. And then we have a bunch of strategies. It doesn't matter what the semantics of those strategies are, as long as they can be used to identify errors in one or the other way in one data set. So you see here, the first strategy is the value alphabetical or not? Is the length of the value shorter than 6? Or is some arbitrary parameter? Maybe we have a knowledge base where we check the value is there or not, right? So for each of those strategies, my value gets an evaluation, 0 if it's not true and 1 if it's true. And we get all these bits. But as you can see, the number of bits and what is set or not does not tell us anything about whether the value is correct or not at this point. But what we can do is we can use these bits to move similar tokens together, ending up with Berlin, Paris together, the missing values kind of together, and Berlin and Paris. So it works out in my tiny example that I handcrafted, that just to show you. So somebody's writing something. They are generated, right? So you just run all the detectors on the data set. They output something for every value, and then you obtain these vectors, right? Okay, thank you for the question. So we end up with these clusters, and now the user just picks some value from each cluster, some sort of representative. You can use different algorithms there to pick the representative. You label it dirty, and then you use the cluster assumption. You say, okay, I propagate the label within the cluster. I'm being a bit over excited here. You see, it could do a lot wrong, but then I can use these labels to propagate and learn the labels of the remaining values. There is also some side problems that we need to solve, like iterative tuple selection. So far we cluster values within a column. And if we want to be user-friendly, we want to show a user a tuple that has all the values together so that the user has some context for labeling to reduce it. So we count our labeling effort on tuple base so that, and that's why we need to pick the tuples in a way so that we pick clusters from each column reasonably. So this is some sort of approximation of the set cover problem. Then we don't have a very fancy solution here, but it works sufficiently well at this point. So should I go to this Lido now, Manuel? Okay. Mario, sorry. Runtime optimize. Okay, so the other thing that you can do is, since you have all these strategies generated, right, and they are very basic, you can try to learn the embedding later, right? So basically you could say, I filter a bunch of them just to reduce runtime overhead, because running all these strategies, there's one resource that we are overusing, that's computing power, right? And computing power can be reduced if we have cleaned similar data sets before. So we can use the strategy filtering approach based on meta learning to get rid of some of them. So we did a bunch of experiments on various data sets that were available, and all the experiments are reproducible according to ACM. And we measured a bunch of metrics like precision recall, harmonic mean between them, and the runtime of our tool. I want to just show you some of them, show some of the results. You see here on the address dataset, the famous one, we compare Raha with a bunch of aggregation techniques. And let me just tell you that the aggregation techniques were outperforming the individual cleaning systems that are out there. And Raha was already with 20 labels quite strong, right, compared to everything else that was there. And the metadata-driven approach is also one of ours. So that's the one where you need like more training data, where we just learn a linear combination between the signals from each tool, where the tools are manually handcrafted for the data set at hand, right? So for Raha, we don't make any assumptions about the tools, but this one, the metadata-driven approach, requires us to manually tune it. Here you see also the impact of strategy filtering. So basically we wanted to improve runtime, and at probably little cost of effectiveness. So on the left-hand side, you see the runtime gain. So it's up to maybe 2 orders of magnitude, depending on the data set that we gain by learning from the past. And on the right-hand side, if you compare, let's say, the dark red part, which is no strategy filtering, and our ones, the green one, you see that we can lose some effectiveness. So more tools are typically better. We also tried out what happens if we pick really most effective configurations per data set. So that's a bit better, but that would require us to evaluate the output of each detector on the data set up front. So this is a fantasy number, so you can never obtain that unless you have run each tool and evaluated the output. So far so good about the detection technique. I will just need to check the time, 9:47. Okay, so let me just move over to the correction approach. So this technique that we have just basically marks some values as errors. So that's basically the output of Raha that we have on the left-hand side. And we have the same labels as before. Now we want to generate corrections that leads to our corrected data. So I have already given some ideas. So basically we are after generating correction rules in a way. So the correction challenges are a little bit different than detection. So first of all, of course we want to high precision, right? But in theory, the search space for correct values is infinite. So we would need to somehow decide what string we pick as the correction. If you're restricted somehow to say, like, that's something what most state-of-the-art tools do. They say all the correct values have to have been seen in the data set before. Then you have no chance to fix values where the correction is outside your data set, right? So you harm recall if you do that. And we want to still have the user being involved with the few labels that they provided. So to solve that, we have a 2-step task formulation. We first use a bunch of base correctors that I will describe shortly to generate all possible corrections for a value. Again, we go for massive computation, right? So we generate all possible combinations here. And then in the second step, using the labels and some learning technology, we try to learn the best correction for an input value. So how do we generate correctors? So again, our goal was to be as general as possible. Typically, you can add correctors as you wish if they fit for your data set properly. But what every data set has for a value is, first of all, the value itself, like the constellation of the characters inside the value give us information. Then, and we can use that to generate all sorts of transformations. Then we have the vicinity of the value. That's all the co-occurring values within the same tuple. So that's basically simulating functional dependencies, if you want, right? So we have that implicitly there. That helps us to generate corrections. And we have the domain as well. So all the values within the same column give us some information about that. So this is like the other dimensions that we have for generating all the corrections. So we use that initially to generate corrections and see how well they can be evaluated. So before that, we have a generalizable abstraction that helps us to update the correctors with the user labels. So that we can say, okay, the user corrected that tuple with these corrections. So how does this labeling, how does this annotations change the output of the correctors per value? So we get a tuple, we clean it, right? So that's what the user does. And then we update our models. And now our classification task is not guess the correction for one data error. It's looking at one data error and a correction candidate at the same time, and with all the model probabilities that evaluate this couple. And then we say it's good or bad. So the prediction task is again a binary one, so it's easier to handle. So we learn that, train the classifier, it works pretty well. We can also pre-train the corrector models. Basically, if you use any sort of data correction in the past, you already can have tuned your model probabilities, right? So you can then use them later as well. So with pre-training, you have higher convergence. Again, a bunch of experiments where we compare additional constraints such as human involvement. Again, just maybe the most interesting example on the flights data set, you see like with the 20 tuples, we are outperforming other existing solutions, in particular HoloClean, which is like one of the state-of-the-art techniques, and also others who use some sort of supervision. So that was basically two tools. Those were two tools that you can use to clean your data set regardless of your application. You just want to find errors and fix them. So you didn't think about the application at all. What we want to talk about now is how machine learning itself influences the output. Right? So first of all, one thing that we need to know is that cleaning data in a production pipeline is fragmented across different roles and different parts of the workflow, be it like data extraction, be it model tuning, be it later monitoring the application, and so forth. So we have a very complex structure, and we might have multimodal or unstructured data. We might have population level errors such as bias, and somehow we want to also be able to clean data that we didn't see before, right? So far our data sets were toy data sets. We had everything in front of us. We kind of could assume that it works when we have seen the data set, but in production, you never know what comes at you, right? What new data sets might come and what data shifts might come as well. So this is a typical process for a DevOps situation. You want to somehow analyze user profiles for purchasing and browsing. So you prepare the data set first, then you try to identify interesting patterns that are good for your model or can be fed there, and then you apply the machine learning model to get all the promotions and alerts for the users. So all the prediction models. And at each step, you see here person, right? So there's a generic person, and they might need to clean the data. So one thing that we were asking ourselves was, does cleaning always lead to better results for the machine learning task, right? So here you see one test example where we have the flights data set and we are comparing the final prediction task results having clean training data versus clean, non-clean test data. And as you can see here, clean is already has the highest probability. So here it apparently seems that cleaning the data helps, although all numbers are low, right? So having said that, it's hard to find a good prediction task where we also have the data for the correction, where we know what is correct and not. So that's the problem why we have this data set, why we don't have a better data set at this point. But we also have a different data set where we can clearly see that cleaning the data is not always leading to better results. So we have a new type of challenge here. So not every error is interesting maybe for our task, but there is maybe also a philosophical question whether it makes sense at all to try to learn from systematic errors in your data. Or maybe you will jump into problems later. Like that's kind of like learning by accident, right? So that's something you want to avoid because it might not generalize at some point. So depending on the type of error and the application, you might do different things, right? So hold on. Oops. Okay. So the question is, how can we leverage the downstream system, be it a machine learning system, to guide the cleaning efforts, to find the right data points to clean and to find the right cleaning treatment, right? So we need to think about how the system would prepare the data and whether the system has access to the entire source of the ML application and which signals can be used, right? So one of the ways to do that is to just use accuracy or any sort of heuristic that is supporting the prediction task. And the other questions are all these assumptions model dependent or independent. So one of the pieces of existing work is choosing tuples based on the gradients, right? How they change. And then it decides to clean training data, right? So it learns and learns, and once the user looks at some data points while labeling for the machine learning task, it notices that something in the training data is wrong and goes back and cleans it. Another approach could be to embed the cleaning operators as operators similar for any other ML pipeline component, right? To include the operators and let the AutoML system decide what to do. So the question here is how you could do that. So if you use a pre-processing model, you would only be able to cover a specific aspect of cleaning, depending on what you have available at this point. Okay, that was my daughter running into the room. But that's something we are right now checking, and we are working on that with several students to figure out what kind of error signals and cleaning operations we can embed in the pipeline and let the AutoML kernel decide. So all of that can then be used, right? So the question is, how can you make the whole system holistic? You would need a bunch of components. So first of all, you would need a set of cleaning operators. That's your cleaning library. You would need some sort of provenance of seeing how these cleaning operators interact so that you could learn how to instrument them into the pipeline. You need to have some interfaces to collect signals such as gradients or other metrics that you collect over time. And you need to have the user to intervene at some point and saying, let's adjust something. And that's something that is quite hard. And we are currently thinking about the reasonable framework for that. But maybe it's also something where there are ideas from the audience on how to proceed and maybe ideas on how difficult it might actually get. to do that. There are also other new challenges for ML, right? So far, data quality only included the very basic dimensions of correctness and completeness. But there are other problems such as population level errors. So what do you do about fairness? How can you measure that and make sure, for example, that your imputation methods do not favor like the most prominent class or group of people, right? So typically when you have data imputation, it tries to learn what the majority does, right? And it amplifies like the bias against the protected groups if you do that afterwards artificially. Then there's other questions how you can maybe embed as an additional dimension new forms of quality, like how do you identify violations against social and cultural norms. There are some groups that are working on, for example, correctness of facts, like looking at data with a semantic combination. All of that are interesting aspects that one can work in future when considering cleaning. Because what we want to say is that it is not enough to consider all of that only in the model, because all of these problems will come throughout the pipeline, like from the beginning, from the extraction until the prediction step. So that is why it makes sense to already think about it a few steps before. So just as a summary, right? I showed you like some state-of-the-art solutions, Baran and Raha, that work example-driven. They use a small number of labels for cleaning. They rely on basic cleaning operators to generalize to many data sets. We have seen that if you do cleaning for an application like machine learning, the cleaning outcome might degrade or reduce the performance of the machine learning application. So that is why it is worth looking at the interaction more deeply, how you can use signals from the downstream pipeline to guide the cleaning process in a more effective way. And that requires to have a holistic view that connects the different phases and parts of the pipeline with each other. One caveat here, or some, like while you're working on automating all of that, one of the things that happens often that I see is that people stop looking at the data themselves manually. And I think generally that's very valuable. So if you have the tools, it does not relieve you from looking at data, right? So that's the thing, basically, the message that might already solve the problem, but the tendency is high that you say, okay, I have the data, I just put it in my MongoDB and I let library X run on it and I look at the results and see what comes out. But I have learned nothing, right? So oftentimes you see major problems with your data set by just looking at a snapshot of the data manually. And that's something that still should be supported in one way or another. And I recommend to any data scientist to do that. So it's always, it's of high importance to know your data, right? So that's what I want to say. Yeah, so there are a bunch of future directions that we are working on right now. So for once, of course, the task-driven data cleaning, that's something that we are working on right now. Then we are thinking about how to deal with data lakes in general. If you have millions of tables, what do you do? Do you start cleaning one table after another and hope that you have some labels for each table? Or do you clean while you're retrieving the data? So there are some questions to be answered here. And finally, the question is, what if I don't want to clean maybe on data source level, but maybe in a later levels when I have the feature construction phase, can I use it as a constraint in my feature selection approach so that I pick features with a certain amount of quality? Yeah, so there's a lot of work to be done yet. With that, I would like to conclude, and I hope that I could upset some people or trigger some questions. Let's see.
Yes, thank you very much for giving this very nice talk. Very interesting.